Alright guys, can everyone hear me? No. Lucky you, right? Yeah, we apologise, our slides are having a bit of a screen resolution problem, so we're going to entertain you with some open office. Right, my name is Werner. This is Nick Walker. We're both studying here at Abertay. We're in our 4th year now, so we've done our 3rd years. We really like to concentrate on areas which don't regularly get attacked. So we've got experience in working with Linux systems in depth. We've done some development on Linux systems. We've done a lot of work in analysing big corporate networks, how infrastructures there work. We've been playing around with Android since 1.5, 1.6 days. And yeah, like I said, we like to specialise in mobile security. Right, so let's start off with a small scenario. Imagine if employee X was to go out to lunch, gets a Twitter notification, Facebook, whatever, finishes lunch, goes back to work like a good employee, and then all of a sudden company X, for whom he works or she, falls victim to data theft. Let's look realistically at what really happened. Employee X actually went out to lunch and fell victim to an XSS attack. This would have triggered a vulnerability, which we'll be discussing in this talk, on the handset, which loads a payload onto the phone, giving us root access to the phone where we can mine off any information. We then installed SOX proxy on the phone, and through the SOX proxy, we managed to push through some of our traffic for basically turning the phone into an attacking platform. The employee then comes in range with the company, connects up to the Wi-Fi by default, and from there we managed to pop a few boxes. And this is all done over 3G and without any user permissions or intervention. Right, so we had to pick a OS to attack basically, and we picked Android mainly because it is open source, so we could have access to all the files, we can enumerate through everything pretty easily. Statistics recently show that there's roughly 300,000 Android phones released, or 300,000 Android devices released every single day. And I think they're currently up to 190 million active Android devices. In this talk we'll go into detail about what versions we cover. You can't really see that, but there's a small little wedge on this pie chart which is not vulnerable to our attack, and it's this little one right here. It covers roughly about 1.8%. 1.8% is not vulnerable to this attack. So currently, so of 190 million, that's about 185 million vulnerable devices to this attack. Yeah, I'll pass you on to Nick now.
Okay, so talk to you a bit about Android, its underlying design. Google's consensus is that Android is not Linux. A lot of people disagree with that and say that anything that runs a standard Linux kernel is Linux, but for these reasons, Google says that Android is not technically Linux. It's based on Linux, but it's not Linux. The security model it uses is the same as any Linux Unix system with GIDs, UIDs, etc. It's worked for 20 years, so why change it now? The reason they say it's not Linux is it's not got a standard set of Linux utilities. There's no text editor in there by default, etc. And a huge amount of tools don't contain the full functionality they do in the GNU toolchain. For example, DD, Echo are all missing various bits of functionality which actually make post-exploitation on this handset pretty difficult. We talk about getting ways around that later. It does run a standard Linux 2.6 kernel currently. I think 4.0 is going to run on the 3.0 kernel, but The difference is it runs with Android-specific kernel patches. It's got alarm driver, a different IPC binder. It's got an extra kernel module called ashmem, which is a kernel-based shared memory that each process can use. So multiple classes that are loaded when you run an Android application can share the same loaded classes in memory, rather than having to instantiate themselves a copy of each. With it being a mobile handset, of course, there's extra power management and lower memory harvest. There's an inbuilt kernel debugger and there's a kernel logger. The main difference, however, is it doesn't use glibc. It uses its own version of implementation of libc called Bionic. So, what's Bionic? Like I said, it's a custom implementation of BSD's libc. It's optimized for embedded use and limited CPU power. It needs to be as tiny as it can possibly be, because the way Android works, the Bionic is loaded into the memory of every single process when it's started. It's not compatible with GNU libc for various reasons. It doesn't contain support for C++ extensions, and has a custom libp thread implementation for various optimizations within the handset. Generally though, within reason, any C or C++ code can be compiled directly against a Bionic using the NDK. You don't have to do any language level changes, because you just can implement and compile against Bionic rather than libc. Okay, so restrictions that Android comes with, an absolute ton of them, to be honest. It doesn't come with a huge toolchain. What is there is a single binary called toolbox, which is symlinked around the rest of the file system. It contains, it's one binary that contains the functionality of loads of the GNU toolchain binaries, for example, ls, pwd, echo, all those programs are within that one toolbox binary. Occasionally, if you've got a rooted handset, hands up who's got a rooted Android handset. More than there was at Brucon, to be honest. They have BusyBox, which has got a lot more functionality than the built-in toolbox, but still has a lot of restrictions in Echo and DB. Next point. Make certain techniques and post-exploitations say a little bit, but it actually made it really quite difficult. I'll pass you back to Werner.
Right, so we've already established that we've chosen Android to be the attack platform. Knowing this, we need to now set this up in stages and figure out exactly what steps we're going to take to gain the access to the phone that we want to get. Right? So we have to find an application or a process running on the phone that's outward facing, and get traffic to that process. What we're covering in this talk, can be done by XSS attacks, emails, phishing, SMS, anything really to... Yeah, and stuff like tiny URLs. If you guys got an email from a friend with a tiny URL saying, look at this lolcat, who here would click on that? I don't believe, come on, I don't believe half of you, right? I would click on it. If Nick sent me a link saying, here's a good white paper, tiny URL, click it, no problem. Okay? Really? Yeah. Right. So then we'd have to gain access to writing file, or gain the ability to write file to disk. This was a little harder and slightly easier than what we thought it would be. Jump out of jail, seeing as every single application within Android is sandboxed. We have to basically break out of that sandbox to gain any functionality on that phone. Jumping out of jail will increase the functionality on the phone, for us at least. From that point, we'll be able to harvest all the data on the phone and start pushing stuff through using a certain technique that we'll be covering to use the wireless interface on the phone. This is just a basic picture of what our setup was like for 99% of the time. I've got my laptop on the right, our victim machine on the left-hand side. That machine is in no way networked to the laptop. We've got our mobile phone at the bottom next to the mouse, and above that we've got a Finera The reason we've got a Finera router is because although this all works through 3G,
3G bills are expensive.
Yeah, we didn't feel that it would be very ethical to pump all this traffic, exploit code and everything over 3G through servers and stuff like that. So we kept it contained by just doing everything over Wi-Fi. It works the exact same way as 3G. Right, so after a lot of scanning, and a lot of scanning and research and stuff, we decided to attack the Android browser. One of the main reasons is because we had to find an application that was running on every single Android device. We couldn't rely on attacking Skype because that doesn't come as default on all Android devices. Whereas the browser, there's always an Android browser. Okay, and the nice thing about attacking the browser is you've got so many vectors that you can attack, plugins. We looked at the rendering engine of the Android browser, which is WebKit. Android uses WebKit, iPhone uses WebKit, and BlackBerry uses WebKit. I'm not too sure if Windows Phone 7 uses it. No. Okay, thank you. Okay, so we established that we're going to attack WebKit, right? And we had to see if there's any vulnerabilities, how hard it would be to find a vulnerability, and it turns out that that's not very hard. These are all CVEs of the past vulnerabilities in 1 year. That's the publicly available ones, yeah. Right, I'll pass you over to Nick. He's going to go a bit more detail into CVEs.
Okay, so there was a few different CVEs we could have chosen with. All of the code, I'll just say before we go into this, all of the exploit code that we use is actually just tweaked public sources to do various different things than they were designed to do. So there's the main CVE, the CVE we actually used was this one. It's a memory corruption in WebKit when it's passing invalid floats. So it triggers when you try to pass not a number. It's a number representation technique. The bug was discovered by Werner from Mozilla and originally exploited by a guy called MJ, who I don't really know that much about. Tweaked by a guy called Itzhak Abraham. Originally, when MJ exploited it, it was about 30% success rate. And then with Itzhak Abraham's work and a few tweaks from us, we've managed to get it to 100% success rate from about 30%. So there are loads and loads and loads and loads of other options, as you've seen on the previous slide. Some of them are, in this situation, leverageable for our technique. Some of them aren't. A couple of other ones that would be viable is the phone-to-own bug that was in the iPhone. As iPhone runs on WebKit, so does Android. You just need to tweak a few return addresses. And that would work in this. Loads and loads of use-after-free and dangling pointer bugs in handling SVG graphics, and that's across the board in all of the WebKit browsers. The only problem with the attack that we use is the return shell is actually quite restrictive. The reason for this is because of the sandboxing. The way sandboxing works on Android is, on install time, every application is assigned a unique user ID and associated with various group IDs for the permissions it's going to require. So if you're in the web browser, you can't see anything to do with the calling mechanisms of the phone or anywhere else. You're trapped within the browser cache, basically. Anything that the browser has access to, you have access to. Out with that, it's really difficult to do anything at all. Believe it or not, when you get a shell back from the web browser, you're actually unable to open OS level sockets, a web browser that can't open sockets, because the calls to open a socket have to be made through the SDK, and when we're doing this, we're native, we're not SDK level, so we can't make open sockets. So in order to get our files across to the phone, we have to do a lot of workarounds. So, I think I've gone too far, yeah? Yeah. Okay, so once we've got our shell on the phone, we need to jump out of the sandbox that we're trapped within. There's a couple of methods to do that. One's within vulnerable user-land applications, like what's the Palo Alto, is it? Yeah. Palo Alto at Black Hat this year demonstrated a technique to get out of the jail by exploiting the Skype application. But like we said, we wanted to do this in stock phones that didn't necessarily have any extra applications installed at all. So we tried to go for a local root technique to try and jump us out of the permissions-based jail. So any standard Linux local root within reason based on the modifications, you have to take it on a case-by-case basis due to the changes in the kernel. Any Linux local root exploits can be ported to Android because it does run a standard 2.6 kernel. There's 2009 proto-ops, no ported reference. That's easily portable. We didn't use that, but I'll talk to you about the one we did use in a moment. Anybody that's got an iPhone that's jailbroken or an Android phone that's been rooted knows that there's a massive community-driven initiative to try and get full access to the handset. And based on that, there tends to be a lot of local roots, and a lot of people that root these phones and jailbreak the handsets don't realise that this is actually malicious code that's exploiting your handset in order to get your own access to the phone. And so there tends to be a lot of publicly available information on how to get root on your handset, which makes our job a lot easier. So, as I said, you have to handpick each exploit based on the circumstance. If you find if there's a Linux kernel local root vulnerability in the pthread implementation, Android doesn't use the standard Linux pthread. You can't pull that exploit. It's not going to work. But various other things have been incorporated, and so it does make certain things easier. The one we used is CD 2009-1185, which attached UDEV. I'll tell you about that in a second. Okay, so there's a few, I'll give you a rundown of the currently available local roots. There's more and more being pumped out every day, but at the time of this talk, these are the main ones. So this is Zygo nproc exhaustion. So Zygo's essentially almost a zombie process that initializes a Dalvik instance. It handles a request for new VMs, which is a request to start a new app, basically. It listens on a socket, and then when it's requested by the OS to fork a new application, it starts a new VM to launch the application. After it started the new VM, it spawns that VM as root for the application, and then after it's instantiated the instance for the application, it drops from root privileges to a secure mode, whichever permissions that application's allowed. So if you open the browser, it starts a root basic application, and then after that has been started and is ready to go and be handed over to the user, that gets dropped to the permissions of the web browser by Securi-TAY. It can be exploited to spawn a root process because on Unix systems there's something called an nproc limit, which is the amount of processes that are allowed to be opened at any one time. So if the nproc limit is reached, the process list is full essentially. The secondary call to Securi-TAY fails, and then Zygo never checks to see if the permissions on that application have actually dropped. So you can actually use a malicious app to force it to spawn as root. Rage Against Cage 2 fills a process list with zombies to exhaust the nproc, kills one, and then starts a new application, and that's spawned as root. The attack also works against something called ADBD, which is the Android debugger daemon, which is what you use when you're debugging over USB to interface with the phone. So those work, but they require physical access to the device or installing a malicious app, which wasn't really what we wanted to do because we wanted to do the whole thing remotely. So we attacked in it. It attacks something called UDEV, which basically is a root level daemon that listens for requests to hot plug devices. For example, if the user in the user interface says mount SD card, okay, that requires root privileges at the OS level. Obviously the user interface doesn't have those privileges. So what happens is it speaks to UDEV and says, I want to mount the SD card, and then the kernel goes, okay, that's fine. What happened was UDEV 1.41 didn't check the origin of the request to a command as root. So large portions of the UDEV code have been moved to init daemon and Android. Android doesn't actually have its own UDEV standalone daemon. It's all been adopted and moved to the init process, which is run on startup. And it included the hot plug bug whereby a user space application could send a rogue request to the kernel and say, can I have this code executed as root? The only difference was the public exploit that's out there is purely used to root handsets, as in like unlock it and allow you to do more than you're supposed to do to your handset. So we needed to modify that, and we modified the payload so that it didn't remount the system partitions read-write and add a SecuID binary to get root. We just modified it to kick back a reverse shell. Okay, so the most current one is Gingerbreak. This is just kind of to future-proof the whole concept. This isn't what we've used, but this works currently. It attacks the Android volume daemon, which it deals with mounting the SD card. It's got a negative out-of-bounds write in an array, and you can using that you can reverse write up in memory to overwrite the global offset table, and it allows you to basically redirect function calls to whichever function you wish. And so it overwrites common function calls like string compare, A2I, and string duplicate, and it points them to system with a pointer to SH. So the next time that vol D tries to call string compare, which is quite often, it will actually start a shell. It works on 2.2 and up, including 3.0 honeycomb. But the only restriction was the calling process needs access to the log group, which the web browser doesn't. So we need to modify that in order to get that working with our current attack. Okay, so
Okay, so we needed to find a way to write files to disk. This was extremely difficult, and then all of a sudden very, very easy, scarily easy actually. A writable directory with an Android is the browser cache. For some reason, we don't know why, they've made the browser cache executable.
okay. So, like I said earlier with the web browser, you can't open an OS level socket. So when you want to write your secondary payload across the disk, which is a local root, it can't be done over a simple socket. You can't do that. So what we tried to do was adopt an ancient technique that was used on Unix mainframes years ago to spoof login prompts. So basically what we did was we tried to use our existing shell that we'd already got back from the exploited web browser and inject echo commands into that web browser, into that shell on our attacking machine, and then write the binaries to disk using output redirection. We tried two methods. Hex echo failed horribly because the echo implementation on both BusyBox and Toolbox don't support hex escape sequence, so it doesn't output as hex, it just puts crap on the disk basically. We did a text file dictionary with, where's he gone? I can't find him. Ian's help, he's in the audience somewhere. Which basically we had a text file for every single byte, unique byte that we could possibly need. So for example, the byte A became 41.txt and 41.txt contained A, the byte for A. And then at the other end we wrote a script that basically carved the binary onto the disk from that essential recipe of ingredients. So byte by byte we started carving it to the disk. It took a long time. Like we overclocked before to a gigahertz from 600 megahertz, and it still took over an hour and a half to write one 100k binary to disk. So it's a slow process. And Unity, after we publicised this, actually came out with a method of using octal echo, which I overlooked when trying to use echo to write it to disk. We didn't like any of these methods, so we went to try and find a better one that didn't take 2 hours to do. So we found a new method to write files to the disk about 20 minutes later. And it was tested and working no matter what OS it was. It works in any of the web browsers. It's an exploited web browser. It works on IE9, Firefox, Opera, Android, Safari, Conqueror, and those are the only ones that we tested. It worked on 100% tested.
Fully updated.
Yeah, these are all fully patched, fully updated. It's a trivial technique as well. It's unbelievable that it actually worked. So,
I hope so.
I hope so too.
Right. So, what we...
Sorry, just very quickly. Did you test it on Chrome?
we didn't. No, we don't test it on Chrome. We'll do that later.
You should test it on
We'll
Chrome.
test it on Chrome later for you.
Yeah.
Okay, so what we've done is we wrote a small web server in C, and all this basically done was served files with hard-coded MIME types based on file extension. Okay, so that means we can kind of just say this file is this, and we promise it is because so says the web server. So we cross-compiled our binaries to run on ARM, and then we renamed them as JPEGs. So we tried to render JPEGs in the WebKit, in the Android browser. And let's give us a little 4 question mark. It's not very clear on the screen, but basically Android's saying, well, these are pictures, but I don't know how to show you them. No problem, right? What this forced the browser to do is it had to download all the data stored in cache in order to render it out. Now that means we've got all of our binary data that's been rendered and stored in cache. Right. From this point, since we've got browser privileges, and as I said earlier, we've got execute privileges. We just chmod our files and execute them. Yeah, and from that, executing our exploit, we get root on the phone. Now, since we've got root, we can now at that point pull any data off the phone. Absolutely anything. We can change data, add data, pull it, you name it, we can do it, right? This includes SMS, emails, contacts. We've got access to all the database files on the phone, so we can change actual core system settings, stuff that even the user doesn't have access to, like geolocation. We can turn on their, check their data roaming, we can change their DNS, absolutely everything. These databases also contain account information with corresponding hashed passwords for that application. We've got access to that. What else are we saying? From this as well, we don't just have access to the data and changing data, we can actually start using functions on the phone. So we can start making silent phone calls on the phone to any number. So if you think of setting up a premium rate number and sending a 1-second phone call to roll over to the first minute of that premium rate, we can hide the call screen, we can mute the mic, we can mute the speaker. So even if the user is looking at their phone, it looks like their phone's not doing anything, but it's currently calling a premium rate number. There is also a file that, for some reason, they've got all the Wi-Fi settings stored in a plain text file or a .config file. Right? So when you open up this file, it gives you the SSID of the access point. It tells you the encryption type. It gives you the passphrase in plain text for that, and it's also got a priority setting. And what this priority setting does is it numbers from 1 up until whatever number, and obviously number 1 is top of the list of priority. So if you're in the range within that wireless network, it will connect to that. But since we can change it, that means we can force people to hop up into our router and sniff all the traffic. And at this stage, basically, if you can write it in C, you can run on the phone.
Yeah. So, how did we make this attack shinier? First thing we did was put in a tiny web server to make it a lot easier to pull config files off the disk and make changes and then drop them back. The main thing we wanted to do when we set out to do this was use the phone as a walk-in attack platform. And so, in order to do that, I modified DropBear, which is a tiny SSH daemon that's running a lot of embedded routers, etc. So I had to put a DropBear key to generate and modify the actual daemon itself. The reason for that was because it supported dynamic socks out of the box, and we can use that to proxy traffic over into the wireless interface over 3G. The main changes that had to be made was DropBear looks for a shadow file, and on Android, because because of the way the permissions work, there is no shadow file. So I had to modify drop there just to ignore that and continue. And then add a master password system. So we can set a master password to access any of the accounts on the phone. So, excuse me. Yeah, so the next stage after that was being able to pump Metasploit traffic over the phone, in over 3G, and then out over the wireless interface using the SOCKS proxy we set up on the phone. So if we connect to the drop there using the capital D switch, which allows us to set up a dynamic SOCKS proxy, we can route the traffic in over 3G and out over a WLAN interface. There are carrier restrictions on that. You can based on which carrier you're using, have the inability to bind listening ports. However, you can modify drop there to connect back to you, so you just do the same thing in reverse, and that would still work. So Metasploit framework actually makes it really, really easy to do all this post-exploitation stuff. You can just set a SOCKS proxy option and then proxy your traffic over the phone. The only issue is it doesn't allow reverse payloads over the proxy, but you can set up an initial bind payload on the target machine, and then use that to set up a reverse connection, so you're not having to continually bounce your traffic over the phone. Once you've got your initial payload onto the target machine, then you can bypass that and go out with the proxy. So we're going to try Gremlin's allowing to do a quick demo for you guys. So if you have a look at what I've got, you can see the drop there, the local root, the web server, and all our various binaries. They're renamed to .jpeg. The simple HTTP server actually does the same thing as our C web server. It serves hard-coded MIME types based on file extensions, so it basically does that MIME type part for us. So I'm serving this is essentially a web server now. So on the phone, if we visit this web server, fingers crossed.
So as we said before, this can be done through tiny URLs or any form that you want anyone to access this page. We've broken up this attack into stages so that we can demo it. We can have this all run through one script and just root the phone.
Okay, so the first stage is the phone connects up and starts downloading our various binaries, because honestly, they are JPEGs. So, there we go. Should end in 404 when it tries to. There we go. Right, okay. Just wait for the phone to catch up. Right, okay. So the phone's actually showing on the screen.
You guys can't really see this up back, but
it's trying to render the 4 pictures that you've seen earlier. And the next stage, we can set up an auto redirect to the next stage of the attack, but we didn't for demo purposes. Just move this over here so you can see what's happening. If you go to the next page.
what this attack's going to do is it's actually going to crash the browser. That's why I'm holding the phone up, so when you don't see a white screen anymore, the browser's crashed.
It's a little slow because the actual exploit is based on a heap spray, but as you can see, we get a connection back 100% all the time. Used to be 30%, not anymore. Yeah, not yet. So we've got our shell back. So now what we need to do, I've written these out already to save a ton of time. So let's have a look at the contents of the web browser cache, and based on size, we can tell that our files have been correctly put into the browser cache. The largest one is actually the drop there SSH daemon, 101 kilobytes. Let's make them all executable. Just double check that went through. Yep, see they're all executable now. Okay, app 43 is the UID of the browser. So let's execute our local root. Is it? Should we show it plugged in? Yeah. Right. So before I execute this local root, I'll just explain to you why there's a cable. The actual exploit adds a hotplug event to the hotplug list, and that hot plug list doesn't get invoked until the kernel next runs a hot plug cycle. And to trigger a hot plug cycle, you have to do a hot plug event. Now that's turning on and off the Wi-Fi, turning on and off the Bluetooth, or plugging in or removing a cable. So just to speed the demo up, that's why we've got the cable. There's no information actually going down that. It's in charge mode only. But the way Android works is when your screen's sat in your pocket for a while and your screen's been off for a while, it turns off your Wi-Fi automatically, which triggers a hot plug event. So it does the same thing, essentially. So I will just set up. Please work. There we go.
The guys here in the front wheel see the phone's actually not doing anything right now. The phone is just sitting idle. There's no authentication needed by the user or anything. Right, we're ready for hot plug?
Yep,
So if you just look at the bottom right hand terminal, so you pull out the cable, it should
Put it back in.
give us back to connection, hopefully. There we go. Right.
Okay, so now we are root system. Root on the phone. The next stage that we wanted to do, we can essentially at this point do anything on the phone, but it's a pain in the arse to use that shell. So we set up a web server. Okay, web server's running. Let's go to the phone. Okay, so now, because this is run from the root directory, we can actually just pass it a full path to any file we want. So, /data/mesh Wi-Fi WPA supplicant.com. That's the actual Wi-Fi file. And there we go. SSIDs, and if this was an encrypted network, you'd see the priority and the wireless passphrase in plain text. We can actually pull off the SMS database. Which is accounts.db. No, that's the accounts database, obviously. Okay, so we can pull all of those off. If you open that with accounts.db, open with SQLite browser. Okay. You can see the first half of my hash password. I'm not showing you the rest. And we can also pull the SMS database off, which I'll show you an old version of it because this is my personal phone. So you can see threads, and you can see contents, recipients, and actually you can set IDs in here. You can set an error flag on one of them. So basically what happens is you can add a message to the database manually and set the error flag, and that basically tells the phone that, oh, you tried to send this before but it didn't work, can you try and send it again please? So basically it sits pulling, and you can actually send SMSs out just by changing the database. You don't have to do any funky stuff, you can just set it as an error flag and it will send out the message. So the next stage that we've done, once you can do anything you want on the phone, that's enough for I think a short time, so I'll run through the next stages. Okay, so we need to generate RSA and GSS key pairs for the sorry. Right, okay, now we're good to go. Right, so we generate the keys you need to run a SSH server. That's the first one generated, the second one takes a little longer. Okay. SS key. And this can be sat in the pocket. No.
Yeah, so the phone's not doing anything, it hasn't been doing anything for quite some time, or not visibly doing anything.
Okay, so now we start a drop-bear server, which is the SSH payment, and we set a master password there. so we can access any account. Please work, thank you. And now, theoretically, if all's gone well, we should be able to SSH into it. So I'll set up the SOCKS proxy on 157, root at 192.168.173. Fingers crossed, yes. Drop there. Now we can do anything we want and we can proxy through the phone. So we do have a really fast video. Do we have time for the Metasploit part of it, or are we short on time?
We don't have it.
We do?
Yeah.
Okay, cool.
We don't have it.
Oh no, but we've got a video recorded of that stuff. I think the font colour is a bit awful. However, hold this fix on the screen. That's horrible. Let's go forward to the point where we start proxying over the phone. Okay, so proxy over the phone. That's awful.
Lights off. These lights up the back. Switches over
Can you see anything there at all?
No.
Try and skip through it. Right, okay, so we set a proxy and then start using Metasploit over the SOCKS proxy. And the exploit going through the bottom. Trust me, it does work.
If you guys would like, we'd show you.
We can show you in the hack lab during the CTF. We can do a live demo if you want. And then we get an interpreter shell back through the target machine. So.
And that's all done through 3G without user permission.
It's on slides. So this is you.
Right, so future of this project. We've got a couple ideas that we're wanting to embrace. Basically, making an attack framework for mobile phones, where this would include attacking other operating systems such as iOS, BlackBerry, Windows Mobile, and something that we'll definitely be looking into very recently will be NFC. NFC is the near field communications. It's basically RFID in phones. So have you guys ever seen the squid cards, payment cards? Paying with mobile phones is essentially what people want to do. We've done some research and we feel there's many mistakes with an NFC, and we feel that we'll be able to find a lot of juicy vulnerabilities within that. Yeah, thank you very much. Any questions?
Have you published this?
We spoke at BrewCon about it a few weeks ago. We contacted Google and their response was basically, so what? This is nothing we've not seen before, because these, like we said, all these exploits are all public, so they already know about them. But the problem is there's the local root exploits that are public and Google are patching out, and there's remote exploits that are public and Google are patching those out. But the problem is it doesn't matter because you can still tie the two together because of the way that the OS is designed. You can still leverage remote root, which wouldn't be possible if it wasn't for various things within the browser cache and stupid mistakes that have been made.
Yeah, what we tried to show within this project was not the fact that, we can make use of exploit codes that are available on the internet. It's fair and well that those exploit codes do work, but we wanted to implement them in a way where it would actually benefit us without having users needing to download an app and install a malicious APK. That's kind of not where we're going with this. The whole point is that we can get access to somebody's phone by them innocently clicking on a link or falling victim to XSS. Yeah.
Did you say there was an Android version that isn't vulnerable to this?
There is, yeah. The latest version is currently 2.3.6. I think 2.3.7 is going to come out soon. That's got Google Wallet. I've been reading up recently, and there is some talk on 2.3.5 being vulnerable. So we're talking a very small percentage, even smaller than the one we originally announced. The latest Honeycomb as well 2 that is not vulnerable.
And the reason it's not vulnerable is because there's no public local route available for those yet. As soon as the community pumps a local route out, then you can just adopt this exact same technique and use it on every single handset. 195 million handsets will be vulnerable at that point.
Any other
Yep.
questions?
It would not just be a simple case of not making the browser cache executable.
Exactly.
But
the-
we feel that I could.
I mean, is there a reason that it needs to be executable?
not that we can see.
Don't take my word for this, because I've been wrong before and I'm sure I'll be wrong again, but I feel that the way that how Google are trying to approach the whole Android operating system, they're trying to make everything seamless and integrated, and if you click on a YouTube link, it opens up your YouTube application instead of trying to render it in the browser. All that kind of stuff, I think, leads to why they need to execute permissions within the browser, especially since you download APKs and stuff like that, for it to automatically bring you back to the APK installer and stuff like that. Any other questions? No. Right, well, thank you very much, guys.